All right, so in AP Stats, it is very important to understand the difference between the distribution of population data, which in practice we never have, the distribution of sample data, which in practice we do have, and the theoretical sampling distribution. So obviously this is what we're talking about right now, but these other things are important as well. By the way, we don't have that sampling distribution either. So if you remember the example we looked at before, this is kind of a picture of those three distributions. This is the population distribution. I don't have the population data whenever I take a sample and estimate the population mean. This is the sample data. This I actually do have. I actually got my 4 people that I selected for my sample. So I do have this, and I do have this 1-point estimator, this one X bar, maybe this guy right here. But I don't have any of the rest of this. I just have my sample and this one value. So this is unknown and this is unknown. It's important that we understand that whenever we're doing these studies. Bias versus unbiased estimators. A statistic, so what is an unbiased estimator? A statistic used to estimate a parameter is an unbiased estimator if the mean of its sampling distribution is equal to the value of the parameter being estimated. If the mean of the sampling distribution is not equal to the parameter, then we say the statistic is a biased estimator. So what does that mean? Well, if this is a sampling distribution of little X bars, so each one of these is a little X bar, if the average of my X bars is equal to the true population mean, if the mean of my X bars is equal to the true population mean, then we have an unbiased estimator. It looks like the center of this is the true population mean, so this would be an unbiased estimator. Over here, if we take a look at the population range, these are probably sample ranges. Each one of these is a little sample range. I don't have a symbol for that, so I'll just write the words down. This is a collection of sample ranges. So the true population range is here. And our sample ranges, if we take a look at the mean of my sample ranges, that's going to be over here somewhere. So the mean of my sample ranges is definitely not equal to the population range. So this would be a bias estimator. Basically, my sample ranges will not be a good estimator for my population range. We actually looked at these graphs in class, if you remember that activity. Which of the following illustrate a bias estimator? I think I explained that. Why? Because the mean of the collection of sample means, X bars, is equal to the population mean. That's what makes it an unbiased estimator, and then over here it would be because it's not. Explain why saying a sample statistic is redundant. Statistic implies sample. When you say a statistic is a measure from a sample. So you don't really have to say sample statistic. Same with population parameter. However, I often say sample statistic and population parameter in class, and I think it's kind of like an educational type of thing. I'm trying to hammer away at the fact that this is, I don't know why I do it, but I can't stop, so just understand that that's being redundant. So this is a little bit BAPS, beyond AP statistic here. But we can finally discuss why we divide by n-1 in the denominator for sample variance. If we sample with replacement, then the sample variance, this formula here, is an unbiased estimator of the population variance, this formula here. So in this one we don't divide by n-1, so that's the population. We do divide by n-1, that's the sample. If you don't divide this by n-1, then this actually becomes a bias estimator of this one here. Meaning, it's actually pretty close. Like if we had a distribution of variances or whatever, the mean of our, the mean if I divide by n is going to be just a little bit off of this one here. So this correction basically makes it unbiased, if you will. Now, there's a lot more to the story here. First of all, we're sampling with replacement, which in stats we don't ever do. So if we sample without replacement, actually, I'm afraid to even tell you what the answer is for that. When we sample without replacement, this isn't even an unbiased estimator of this, but we'll just leave it at this. Come talk to me if you got some more questions or want to dig into it. I got some activities I can show you to help highlight it all. Okay? Variability of a statistic or a point estimate. So, when we estimate a parameter from a statistic, we want to be assured of two things. First, is the collection centered about the right spot? Is the center of my sample statistics equal to the population parameter I'm trying to estimate? That means it's unbiased. But a second and equally important thing is how close is the parameter. How close to the parameter is it likely to be? So how close is our statistic to the true parameter? How spread out are our statistics? Are our statistics likely to be here and here? Or is it possible to get a statistic that's way out here? Or are they really all going to be very close? That's important because it tells us how good of an estimator our statistic is. When we report an X bar, the thing that people should be interested in is how close is that sample mean likely to be to the true parameter? People love thinking that, oh, if my sample is 72, then that must mean my population mean is 72. Well, no, we know it's probably not. The question is how far away is it from the true value? So, as we discussed in various activities in class, if we increase the sample size, this will decrease the variability of our sampling distribution. If we increase our sample size, it'll give us better estimates. Suppose exactly 75% of a school of 2,000 students think Donald Trump is the best presidential candidate to come along in the last century. By the way, I apologize for the tone of this. It sounds like it's being a little bit, I don't know, sarcastic is the word, but this was an example that I used like 3 years ago when Donald Trump had just announced his presidency and people thought it was kind of a bit of a ridiculous type of thing, or they didn't think that he would actually become president. So don't read too much into that, please. So we're interested in what the sampling distribution of sample proportions will look like for sample sizes of 100 students and 300. So we're taking samples of size 100 and we're taking samples of size 300. We have 2,000 students in the population. So there's 2,000 students in the population. We're taking samples of size 100 and 300, and we're going to calculate the sample proportions. So for example, now the true proportion is 0.75. Now one thing we haven't really talked about is that if you take a good sample, your sample proportions are going to be an unbiased estimator of the true proportion, of the population proportion. And you can kind of see that here. This is the true proportion, and it looks like our p-hats, each one of these is a little p-hat. It looks like our p-hats are centered about the true proportion. So it's unbiased. That's good. But notice how spread out it is. It's pretty likely that we would be 5 percentage points off. Or not really even that unlikely to be even 10, well, it's possible to even be 10 percentage points off. Or in this extreme case right here, it looks like we're actually like 18 percentage points off, but that's pretty rare. We did 200 samples, so this only happened once out of 200. So, but for the most part, we're about 5 percentage or 10 percentage points off on average, maybe. Well, what if we take sample size 300? Notice we're still unbiased. The center of my sampling distribution is still the true population proportion, but now my p-hats are a lot less variable. That's just common sense, right? You survey more people, you're going to get a better estimate. Your sample proportion is going to be closer to the true mean. So we can kind of see that this one's less variable. Now, it's pretty unlikely to be over 5 percentage points off, whereas here, it wasn't unlikely at all. So I don't know if you guys are kind of connecting the dots here, but the standard deviation of this sampling distribution is an indication of how close our sample statistics are likely to be to the true population parameter. If we have a lot of variability, then our p-hat might be off by quite a bit. If we have a small amount of variability, then there's a good chance that our p-hat is going to be relatively closer to the true proportion. So bigger sample size gives us better estimates. Why? Because of the standard deviation of our sampling distribution. So the variability of a statistic is described by the spread of its sampling distribution. This spread is determined mainly by the size of the random sample. Larger samples give smaller spreads, give better, closer statistics that are likely closer to the true mean, true proportion, true parameter. The spread of the sampling distribution does not depend much on the size of the population, as long as the population is at least 10 times larger than the sample. So we talked a little bit about this in class, this little idea right here. And it's a little bit tricky here because I want to be right. I don't want to lead you astray. But in general, it doesn't really matter what the population size is. Your population size could be 1 million. And this population size here could be 10,000. And if you take a sample of size 200 from this population and a sample of 200 from this population, a lot of people would think, well, this is going to be a better estimate because you're taking a higher percentage of the population. But that's not really true. These are actually going to be equally accurate estimates because it really just depends upon the sample size of the size of your sample. It doesn't matter what the population size is. Now there is more to the story, and this is obviously referencing the 10% condition. But I'm not going to go into it too much right here. Again, come talk to me if you want to talk a little bit more about it. But if the 10% condition is violated, then what I kind of said right here isn't really true. But when the 10% condition is in effect, these are basically going to be equally good estimates. Okay. Caution: taking larger sample sizes does reduce the variability of the statistic. However, it does not fix bias. Doesn't matter how big your sample is. If you got a bad sample, then you got problems. And I'm talking about bias caused by bad sampling, not bias and unbiased estimators. But if you take a bad sample and it's not representative of the population, then it doesn't matter how big your sample size is. It's going to be kind of a wasted data. All of the examples of sampling distributions were generated using a simple random sample technique. All the ones we've been talking about are assuming you did a good sample. If you do not use a good sampling technique and have bias due to faulty sampling techniques, your point estimate will be off regardless of the sample size, and it's hard to predict how off it's going to be. So just a reiteration of what I said up here is the population size has little effect on the variability of a statistic, assuming the 10% condition is satisfied. Okay? All right. It's a good place to stop. We'll do this next example in the next video.